Hello, and welcome back to the Cracking FAANG YouTube channel. Today we're going to be solving Leetcode problem 1339, maximum product of split binary tree. Given the root of a binary tree, split the binary tree into two subtrees by removing one edge such that the product of the sums of the subtrees is maximized. Return the maximum product of the sums of the two subtrees. Since the answer may be too large, return it modulo 10 to the 9th plus 7. Sorry, this should be 10 to the 9th plus 7. Note that you need to maximize the answer before taking the modulo and not after taking it. So for example, if we're given this binary tree 1, 2, 3, 4, 5, 6, how can we split this? Well, if we look, essentially what we want to do is we want to figure out all the possible sums of our binary tree and then multiply it by the other side. So for example, if we were to just take this node 4, we would multiply it by the product of everything else. So the sums. So 5 plus 2, 7, plus 1, 8, plus 3 is 11, plus 6 is 17. So that would be one product. Then we could do 4 and 2. So 4 plus 2 times, the rest here. And then we could do 2 plus 5 plus 4 times, whatever. And basically we want to go through all these possible options and find whichever one gives us the largest amount. So how do we want to do this? This seems a bit complicated at first, but what we want to realize is that if we have the total sum of our tree, so this is the sum over all the nodes, we'll call this the total sum, right? This is just the sum of all the nodes. Then what we want to do is if we have each individual sum of the nodes, right? Like assuming that we cut it somewhere, so like this tree and this tree, then all we need to do to find the other side of the tree is simply to take our total sum, subtract it from whatever our current sum is, and then we just multiply that by our current sum, and that will give us the product of the binary tree. So essentially that means that we need to do two things. We need to first figure out the total sum of the binary tree, which is easy to do. And the second thing is we want to figure out all sums in the binary tree, right? So every possible combination that we can make here in our tree. So for example, we could have just the node 1, we could have the node 1 and 2, we could have 1 and 3, we could have 1, 3, and 6, 1, 2, 1, 2, 4, basically all the possible ways we could do this. And since we're looking at exploring all possible trees on our path, this is going to indicate that we want to do this in a depth first search manner. So we're going to store all the possible sums. And then for each sum, we're going to run this computation, and this is actually going to give us our maximum. So if that doesn't make sense, let's actually go to the code editor and you can see how it's implemented. This is actually a really straightforward problem and it's not that bad. I think that once you see the actual solution, you'll understand how to solve this, and it's quite easy. So let's go to the code editor instead of trying to look at this spaghetti diagram that we have over here. Let's test. Okay, we are in the code editor. Let's write the code. Remember that we need to calculate all the possible sums in our tree, and we're going to use a depth first search to do that because depth first search will give us all possible paths along the tree, and we just need to sum the paths. So we're going to say tree sums. We're going to define a empty list here to store our tree sums, and we're going to define our depth first search function, which is going to take a node, and we need to now process this node. The first thing that we want to do is actually make sure that we handle our base case, in which case the node is empty. Obviously there's nothing to sum if it's empty, so we just return 0. So we're going to return 0. So obviously this is when we hit a leaf node, or we hit a node that doesn't have any children, or may not have a left and right child, and if we try to go into it, then obviously we can't sum something that doesn't exist. So what we want to do now is we want to do this in a post order manner. So we want to process the children first and then our node. So we're going to process the left child. So we're going to say so we're going to call DFS on the node.left, and that's going to give us our left sum. The right sum is going to come from node dot right, and then we're going to get the current sum, which is going to equal to our left sum plus the right sum plus whatever our current node's value is, and that's going to be our current sum along the path. So obviously we build this in a bottom-up manner. So we traverse down, we hit to the 4, we sum that, that's one sum. We get to the 2, we add the 5 to it with the 2, and that's another sum in the tree, and then we go up, and then on and on and on. So we're doing this bottom up. So we then say tree sums dot append. So we've now found a new sum for one of our trees. We're going to say cur sum. We're going to append to the tree sums, and at the end we just want to return our current sum, and that's going to get passed up to the next level and stored in either left sum or right sum. So that's the DFS function, pretty straightforward. Now what we need to do is we need to actually call our DFS function, and at the end, obviously, since we do a bottom up, by the time we exit from our root node, our cur sum variable will actually be the total sum of the tree, which remember we need to actually do our computation here. So we can say total sum is going to equal to DFS, and we're going to call that on the root. So if the root is empty, then we'll just hit this, we'll return 0, and we are done. We don't need to really do anything after that, although we'll kind of go through a little bit of logic here. So we're going to say max product. It's going to be 0. Obviously, we haven't seen any product yet, so it's going to be 0. And we're going to say for each sum in tree sums, what we're going to do is we're going to say that the maximum product we can get is going to be the maximum of whatever the current max is. So max product. And then what we want to do is we want to say sum times the total minus the current sum. So if current sum represents the sum of our tree, so for example, if we were to split it at this red line, it would be 2, 4, and 5, that sum, then the sum of the other side is going to be the total sum of the tree minus whatever these nodes is, right? Because obviously that's how addition works. We can add these two pieces together to get the total sum. So obviously those are going to be our two sides, and then we just multiply them together to get that product, and then we take the maximum of that product, or whatever the current maximum is, whichever one is larger, and we do that for all the sums in tree sums. Then remember that the last thing we need to do is actually return it modulo 10 to the 9th plus 7, because the answer may be too large to return. So we're going to simply return max product modulo, let's see, 10 to the 9th plus 7. Cool. So let's submit this, make sure that it works, and total is not defined, of course. Total sum, whoops, okay. And there we go. Okay, cool, it works. What is the time and space complexity for our algorithm? Well, to do a DFS through any tree, and we're doing a post-order traversal, but that doesn't really matter. To do the traversal is going to cost big O of n time, because we have to visit every single node. And to then go through all the sums is also going to be big O of n time. So we're looking at, 2n, but asymptotically, this is still big O of n. Space complexity wise, obviously we have the recursion stack inside of our post order depth first search traversal, which we can think of big O of n, where n is the number of nodes in the tree. And then obviously we need to store all of the sums, which is going to depend on how big the tree is, which is going to be big O of n. And again, we have 2n here, but asymptotically, this is just going to be big O of n. So that is going to be your solution for this problem. Really straightforward. It's just a simple post-order traversal. Process the left and right children, then process the node, and it's pretty straightforward. Not really too many tricks here. Traverse the tree, then just handle the sums. Really easy. So hopefully you enjoyed this video. If you did, please leave a like and a comment. They really help with the YouTube algorithm. If you want to see more content like this, please subscribe to the channel. Otherwise, thank you again for watching. Have a nice day. Bye.